Hello everyone, my name is Ashkan, and in today's tutorial I'm going to share one of my recent experiences in material selection for a low temperature vessel carrying hydrocarbon gas with you. Before starting this video, please subscribe my channel because it gives me more energy for continuing this path. Okay, well, recently in one of our projects we had to construct a pressure vessel with the following process characteristics. Based on this table, the operating pressure is 2 bar gauge, the design pressure equals to 5 bar gauge, the operating temperature, maximum design temperature and minimum design temperature are 62, 100 and minus 62 degrees centigrade respectively. The gas and liquid density and flow rates are also mentioned in this table. The vessel's dimension and application are also specified here. Okay, well, it seems that we have all the required data that we need for doing a material selection for our pressure vessel. First of all, we need to have an overall plan of what we are going to do. As you can see in this slide, the first step is analyzing the corrosion factors and selecting the main material of the vessel. We need to find out the material is carbon steel, stainless steel, or other CRAs. We are not focusing on non-metallic materials here. Secondly, the corrosion allowance of the selected material shall be specified. And finally, we need to specify further requirements of the material. The rest are items such as HIC, SSC, impact, PWHD, or other features that are required for being assured about the material. Finally, the exact ASTM grade for plates, pipes, forging, and fittings need to be clarified from ASME B31.3, Table A1 for construction engineers. So let's get deeper into the first step, which is selecting the main category material of the pressure vessel. To do this, we need a corrosion analysis software. I usually use one of ECE or Predict softwares for my job. Here I am going to use ECE 5.3 for checking the most appropriate material for my project. As you may know, the material selection must be always done considering technical issues, cost, market, and construction difficulties. To cut it short, let's just open ECE 5.3 and start to fill out the blank cells. As my project can be considered more similar to the right box, I select the flow line corrosion evaluator and not the tubing project, which is mostly related to downhole tubing of an oil and gas wellhead. Before starting, just have it in mind that ECE anticipated corrosion rate is by assuming the carbon steel material and not the stainless or corrosion resistant alloys. Okay, by selecting the flow line project, a box like this will appear. Firstly, we should specify the outside diameter of our pipe, which is a vessel here. You may ask, are the flow line and the vessel exactly the same in corrosion analysis? The answer is clear, no. These two has different features in corrosion analysis, but as we have limitations in corrosion analysis software for equipment, we have to do just an estimation of corrosion probability in our system. And what I'm doing here is finding the overall reaction of the fluid with carbon steel in a somehow similar environment, in my pressure vessel. Okay, let's get back to the analysis. The outside diameter of pressure vessel is around 1.5 meter. Let me clear something here. In some cases that the OD of the pressure vessel is too large, you can use the corrosion analysis of the inlet and outlet pipes and extrapolate them into the pressure vessel to understand the corrosion rate of the vessel. But here the OD is not too large and I prefer to put it exactly into my software, like I'm considering it as a pipe. Okay, well, the OD is 1.5 meter, the thickness of the pressure vessel is 11 millimeter as I inquired it from the mechanical group, and the length of the pressure vessel was 4.5 meter based on the table in previous slides. As you may notice, since this module is generated for pipe and corrosion estimation, the software automatically changed the length to 100 meter. This is not too important in our current case. We are using the software just to understand the tendency of carbon steel to be corroded in contact with the process gas. Finally, the carbon content of the pressure vessel, which is limited to 0.23% in wet sour services. This cell doesn't have direct contact on corrosion rate. However, I will provide a tutorial and there I will tell you the exact limitations of the carbon steel chemistry in sour services. The items such as sulfur, phosphorus, and carbon equivalent quantities. Now let's go to the next step, conditions. Here the first item is the temperature of our environment. As we are not analyzing a pipeline, the inlet and outlet temperature and pressure are the same. So let's find out the cells based on the data provided in the input slide. The temperature is 62 degrees centigrade and pressure is 2 bar gauge, which is equal to 3 bar absolute. As you understood, I'm not using the design data. In corrosion analysis, we always use operating data as the system is facing with operating condition most of its design life duration. The corrosion is not a sudden accident like what we do in thickness calculation of a pipe body. It requires facing with corrosive components during a long time to happen. Anyway, the next item is CO₂ concentration, which is 3.5 mol% in our project. H₂S is also 1.4 mol% according to the received data from process department. And in the water chemistry section, the salinity and bicarbonate quantities equal to 0 as we have an associated gas in our project. Now let's fill out the flow rates. The liquid hydrocarbon flow rate is 150 standard barrel per day. I don't know the exact API gravity of the fluid, but as it is a liquefied natural gas, I take it at 50. The higher is the factor, the lighter is the liquid. The next item is gas flow rate in MMSCFD, which is 1 in our project. And finally, water flow rate in standard barrel per day, which equals to 30. All the cells in the advanced tab will remain empty as we are not using corrosion inhibitor or glycol in our vessel. I prefer to have all the other cells empty. I don't want to make it difficult at this stage. We will have another comprehensive tutorial about ACE, and there I will explain the rest boxes in the software. Now, as you can see in the right box, the uniform corrosion rate is predicted to be near to 0, while the pitting rate is 0.006 mm per year. Considering 20 years of the design life for this vessel, the overall corrosion rate during the whole design life would be 0.12 mm, which is negligible. So carbon steel will be our best option in this project for all sections, including shell, head, nozzle fitting, or etc. So as we usually use 1.6, 3 or 6 mm of the corrosion allowance typically, 1.6 mm can be chosen here. In some company practices, you may find that the corrosion rate of the fixed equipment shouldn't be less than 3 mm for the sound services. We respect those documents. However, in our project, we prefer to keep thickness as low as possible because we have a cryogenic service gas. You will understand more followingly about thickness effects on cold cracking, but generally when the thickness increases, the cracking probability goes up accordingly. Typically, we give the corrosion allowance to the mechanical groups they use in their thickness calculation. We did it in our project, and the thickness that came out from the mechanical department was 11 mm, considering pressure, temperature, occasional cases, corrosion and construction allowances, and etc. In other words, our nominal thickness is 11 mm. As we now are aware that carbon steel with 11 mm of thickness is our choice, the next step is specifying the exact UNS or ASTM grade of all components in our vessel. The first items are shell and head material. Usually in our market, in my country at least, we use some typical plate materials in different projects, which are ASTM A283, ASTM A516, ASTM A203, ASTM 537, and some other grades. But between all of them, ASTM A283 and ASTM A516 are easily available in the market. We also knew that the minimum design temperature would be a challenge in material selection. So let's first of all open ASME B31.3 table A1 to see the limitation of each mentioned plate material in low temperatures. As you can see, most of the plate grades minimum temperature have letter A in front of them. If you don't know what is the meaning of these letters, watch my full video on impact testing requirements. I will put the link above. So we are looking for letter B or C that is mostly observable in front of ASTM 516 plates. It is also a common plate for vessel construction, so why shouldn't we try our chance? Let's try. Maybe it can be our material for that minimum design temperature. In similar cases, I usually start by checking ASTM A516 grade 6C. As you can see, the letter in front of this material is C. Now let's go to figure 323.2.2a of B31.3 and see what is the minimum temperature of this material without impact testing. According to this figure, when the material has 11 mm thickness, the minimum temperature would be almost minus 45 degrees centigrade. You can have a look on the related tabular values in 31.3 for finding the exact numbers. Anyway, I want you to notice to note 4 of this figure, which tells us that for all normalized grades of ASTM 516, curve D can be used. So, minus 48 degrees centigrade is the minimum temperature that ASTM A516, any normalized grade, can be used without performing impact testing. But as you noticed, our process design minimum temperature is minus 62 degrees centigrade, which means we need to either change the material or do the impact testing. For finding the solution, let's review the statements of the code. The first step for this purpose is checking the table 323.2.2. Our material is from the third row of the table and our technical condition is from column B. According to box B3, when we are using a carbon steel material in a temperature below the mentioned temperature in table A or the figures we reviewed, we have to accept as provided in note 3 or 4 that we will review subsequently, heat treat the base metal, then impact test the base metal has and weld deposit. It again mentions that when the material is planned to be used at temperatures below the assigned curve, the weld and has shall be impact tested. Up to now, we are sure that the base metal in suppliers or manufacturers' shop shall be impact tested. Have it in mind that we are not talking about the details of impact testing in current video. You can check my other video with the link above. Now let's review the referred notes in box B3 to be sure that we are not missing anything. Note 3 tells us to see paragraphs G through I of section 323.2.2. I've provided the mentioned notes here. Note G says that if the stress ratio is below 0.3 and the minimum design temperature is warmer than minus 104 degrees centigrade, impact testing is not required. It is getting interesting, no? It is somehow exempting us from doing impact tests, which reduces the time and cost of the project. Let's find the stress ratio figure, or in other words, exemption figure in ASME B31.3. Here is the figure, and we will understand how to use this curve for impact testing exemption followingly. You can also use ASME section 8 division 1 UCS 66 for this purpose. Both of them will reach to the same result. Anyway, whether using 31.3 or section 8, we want to find out if we are exempted from impact testing or not. The vertical axis of this figure is the ratio and the horizontal axis is the exemption temperature. I've described this figure thoroughly in my other videos. We are just using it now. I've previously inquired the amount of ratio from mechanical department which is obtained from PV Elite software. Accordingly, the ratio is almost 1 in shell and head and almost 0.5 in nozzles. So let's get back to the B31.3 or section 8 figure. Based on these figures, as the ratio equals to 1, we cannot use any amount of impact test exemption. If it was, for example, 0.7 for shell and head, we could use ASTM A516 grade 60 normalized material almost at 16 or 17 degrees centigrade below minus 48 degrees centigrade determined in curve D of 323.2.2a figure. Then we could use that material at minus 62 degrees centigrade, which is our minimum process design temperature without further impact testing. The next note, which is note H, tells us 2 important points. First, it tells us that if you want to use the exemption curve, the lower acceptable limit of using a material without impact testing is minus 48 degrees. In another word, you can use exemption figure, however, it cannot be used at temperatures cooler than the minimum design temperature of minus 48. If your minimum design temperature is minus 62, in our case, for example, you have to do the impact testing. You can pause the video and read the exact test from the code. Then resume it to see how we extract interpretations from it. The second part of this note talks about the well deposit of carbon steel materials. When it is mentioned necessary to do the well impact testing in accordance with box A3b of table 323.2.2, the exemption curve is not applicable at temperatures colder than minus 29 degrees. So up to here, we are condemned to do the impact testing based on the notes G and H. Let's proceed and see if the last note, note I, can help us to run away from impact testing or not. Before talking about note I recommend you to pause the video first, read the note yourself, see what you understand from the note, then continue watching the video. In addition, do not forget to subscribe my channel and like the video while having the video paused. Anyway, note I tells us that when you perform the impact testing and you also wanted to use your material below the impact testing temperature, you're allowed to use the exemption curve just up to minus 108 degrees centigrade temperature, and not colder than that. For example, we are buying a plate material that has been impact tested by the supplier at minus 48, and your minimum design temperature is minus 62, like my case. In this way, you're allowed to use the exemption curve up to minus 108 degrees centigrade if C applies. You might be curious that what is note C that has been referred twice in the last couple of minutes in this code. Let's have a look at it together. Note C is for making sure that the material, which can be a valve body, fitting, flange, or even a plate material, is not planned to be used in severe operational and maintenance conditions. For example, conditions such as high temperature, local stresses, or high maintenance loads such as a high torque required for closing or opening a valve during low temperature operation. Naturally, in these cases, a higher stress is applied on that material, piping or mechanical component that may cause a crack initiation or propagation. The next referred note under the table 323.2.2 was note 4. This note is talking about the limitation of choppy test specimen dimensions, which is not our concern here. As our sheet plate has the thickness of 11 mm, we definitely can cut out the specified specimens of it according to the test procedures. Reading and analyzing all the above notes led us to understanding that ASTM A516, grade 60 normalized, which is our most suitable candidate material, must be impact tested on the base metal, well deposit, and HAZ area in procurement documents and also in projects WPS and PQR. We couldn't exempt the material from being impact tested. As I told you, we are not talking about the procurement details, mill certificate, WPS, or impact testing details, since they need a comprehensive separate tutorials. Also have it in mind that as I previously worked on other projects and inquired from other material engineers, I'm somehow sure that ASTM A516 grade 60 normalized can pass the impact test at minus 62 degrees. Otherwise, if it couldn't pass the test under any condition, we need to change the material to other grades, such as ASTM A203 grade E or grade D, as they are definitely working at cryogenic circumstances. The next item that we have planned for discussing is pipe. As you know, in carbon steel piping systems, there are some popular grades such as ASTM A106, API50, ASTM A53, and etc., which are mostly used between engineers. Our first try is checking whether these commonly used materials can meet our cold temperature requirements or not. To do this, we need to go to ASME B31.3, table A1, to see their minimum temperature column. Here, for better understanding of the tutorial, I decided to open the code and review the grades and materials directly here. First, let's search pipe in table A1 to find the pipes category. Here is pipe and tubes. ASTM A106 grade A follows curve B of 323.2.2a figure. ASTM 106 grade B has also the same cold temperature limitations. API 50X52 follows curve A. Okay, as you can see, not only ASTM A106 and API 50 pipes, but most of the pipe materials specified here in this table have the minimum temperature limit of minus 29 degrees, or follow curve B or A of figure 323.22a. The only materials that can be used in low temperatures are various grades of ASTM A333 material. Anyway, let's check figure 323.22a to see what is the minimum temperature of curve A and B. As you can see, minus 10 degrees for curve A and minus 30 degrees for curve B are much warmer than our process minimum design temperature, and so those materials we reviewed in table A cannot be used except as ASTM A333. For deeper checking of these materials' features, let's open the related specification to see the exact temperature that the material can be used without further impact testing. I previously downloaded the standard specification. As you can see in table 4 of this specification, different grades of ASTM A333 material are previously impact tested, and their application at these temperatures is already confirmed by the manufacturer. Among the mentioned grades here, grade 3 and 4, grade 7 and 8, grade 9 and grade 11 have the impact test temperature at cooler temperatures in comparison to our process minimum design temperature, which means these grades can be used in our project. As we have an available market of ASTM A333 grade 3 in our country, here we can decide that this grade is the most suitable material for our project. So let's write it down in our table in PowerPoint slide. We could also use other grades such as grade 6 with impact testing temperature of minus 45 degrees centigrade by the manufacturer, and then either do the impact testing at minus 62 or use the exemption tables and figures in the code to use it in as received condition. It usually depends on the cost, time, and the decision of the designer. Here we prefer to use grade 3, which completely falls inside our margin. The next items are flange and nozzles of the vessel. As you know, these items are made with forging manufacturing process. As a result, we need to find the forging category inside table A1 of ASME B31.3. Again, let's search them. Forging and fittings are at the same category in the code, so you should already know which grade is forged and which one is fitting. Anyway, I already highlighted the candidate materials which can be used for our process gas considering the minimum temperature column. Some of the items may have the minimum allowable temperature warmer than the process minimum design temperature. In these cases, we have to do the impact testing, use the exemption curves and figures, or select the materials with minimum allowable temperature colder than the process minimum design temperature. However, generally, the material's minimum temperature is mostly minus 20 or minus 50 degrees Fahrenheit, or follows curve A and B, which is not useful for us. Have it in mind that when checking the forging and fitting ratio in piping systems, the ratio that must be used for impact testing exemption, I usually use scissor 2 for checking the stress ratio and on that component, and not PVL it like what we did for shell plate in the pressure vessel. Anyway, here you can see ASTM A420 WPL6 with minimum allowable temperature of minus 50 degrees Fahrenheit, or ASTM A860 WPHY42 or 51 with minimum allowable temperature of minus 50 degrees Fahrenheit. All these mentioned materials are fittings. ASTM A350 LF2 is a forged item that can be used for flanges and nozzles, and its minimum allowable temperature is minus 50 degrees Fahrenheit, which again needs to be impact tested to be used at minus 62 degrees centigrade, which is our process minimum design temperature. Anyway, let's proceed to see if we can find another material. Here, as you can see, there are two materials, one forging and one fitting, that both have minimum allowable temperature of minus 150 degrees Fahrenheit, which almost equals to minus 100 degrees centigrade. As you might know, adding some nickel to the chemistry of the carbon steel materials can considerably enhance their minimum temperature capabilities. This can be seen here as both ASTM A420 WPL3 and ASTM A350 LF3 as fitting and forging materials have some nickels in their metallurgy. As I told you previously, if not possible for you to procure these materials for your project, you can use other materials with minimum allowable temperature warmer than the process minimum design temperature, either with or without impact testing. For checking whether impact testing is mandatory for your case or not, you need to read and understand Chapter 3 of ASME B31.3. Then you may use the exemption conditions for your scenario. As you saw, ASTM A420 WPL8 was also an overqualified candidate among the options in Table A3 of the code, which we are not using it here. As a conclusion, ASTM A420 WPL3 would be our fitting material and ASTM A350 LF3 would be our forging material for nozzles and flanges. Welded internals are the next step of our material selection. You definitely know that the vessel's internals are components that are in contact with the process fluid, so corrosion risk is a major issue here. Naturally, under these kinds of circumstances, the material engineers usually prefer to select CRA materials such as stainless steels. But welding a stainless steel material to the vessel's carbon steel plates would definitely increase the galvanic corrosion risks, which is not favorable here. As a result, although the corrosion of the internals is an important factor, but we prefer to use a carbon steel material to prevent other types of challenges in our material selection. Considering these explanations, the welded internal must be from the same grade and material of the vessel's sheets and plates. So ASTM A516 grade 60 normalized with impact testing at minus 62 degrees centigrade would be our choice. In some cases, the internal might be manufactured from forging, pipe or fitting, then the material ASTM grade will be changed accordingly. The bolted internals against the previous row can be selected from CRA categories, as they can be isolated from direct contact with the vessel's body by the use of washers or gaskets. As a result, here we need to select the type of the CRA for our bolted internals. For this purpose, let's open the material evaluator of ECE to see which type of CRAs is the most suitable candidate for our process condition. To do this, open ECE and make a new project. Click on the fill line project. Then click on the fill line CRA evaluation at the top. This module helps you to check the corrosion or failure probabilities of your candidate CRA in process conditions. Here we remembered from the beginning slides that the operating temperature is 62 degrees centigrade. The operating pressure is 2 bar gauge or 3 bar absolute. The CO₂ mole percent is 3.5 and H₂S mole percent is 1.4. No salts were reported in the input data from process department. Adding all these quantities in the CRA evaluation modules shows us the martensitic stainless steels such as AISI 410 or 13% chrome stainless steels are a risky option. The first safe material for our process condition is stenitic stainless steels or SS316. So without focusing on the exact ASTM grade of the bolted internal, let's write it down in our table. As a material engineer, we don't know the type and geometry of the internal exactly, so it can be forged, plate or etc. Then the mechanical department will specify the exact ASTM grade based on their application. We just write SS316 here. Most of SS316 grade materials have minimum design temperature far colder than our process minimum design temperature. So it seems that no concern would exist for impact testing of 316 materials. To be sure, let's check it on table A1 of ASME B31.3. I searched 316 on the first page of A1 table, as you can see, the pipes and tubes of 316 have the minimum temperature of minus 425 degrees Fahrenheit. The next category, which is plates and sheets, ASTM A240, for example, also has the minimum temperature of minus 425 degrees Fahrenheit. It is almost the same for 316 forging and fittings. The next step is specifying of nuts and bolts materials. For this purpose, we have two important factors we need to consider in our material selection. The first one is our process gas is sour. The bolt and nut material must be ASME B31.3 qualified. Then it must tolerate our low temperature conditions. Let's open ASME B31.3 standard to see the pre-qualified nuts and bolts grades. Now just search bolt. As you can see, here are some nuts and bolts acceptable materials by NACE. Let's find these grades in table A1 of ASME code to see if they meet our low temperature requirements or not. The first one is ASTM A193 grade B7M. Here it has minimum temperature limits of minus 55 degrees Fahrenheit, which almost equals to minus 48 degrees centigrade. The next material is ASTM A320 grade L7M, which has minimum temperature limit of minus 100 degrees Fahrenheit, which is equal to minus 73 degrees centigrade. That can be suitable for us. So the bolt material is selected, and it is ASTM A320 grade L7M. But what about nuts? Two grades of nut material are also specified in NACE, ASTM A194, grade 2HM, and grade 7M. This is the first one. And here is the next one. As you can see, both of them has the minimum temperature limit of minus 55 degrees Fahrenheit, which is not suitable for process gas conditions. Here I have an important point. Based on the information received from other process departments, the minimum design temperature condition only occurs during depressurizing scenarios, and it may happen less than 10 times during the whole 20 years of the design life. Each depressurizing duration is less than 1 hour, so as our pressure vessel is not in direct contact with low temperature process gas, but it is always in contact with H₂S containing sour gas, I prefer to prioritize NACE requirements instead of low temperature conditions. Again, between ASTM A194 grade 2HM and grade 7M, I prefer to select grade 7M as it is an alloy steel and can definitely have better low temperature properties. As a result, our nut material would be ASTM A194 grade 7M. The material of supports and skirts on the next step should be specified. Since the supports and skirts are directly welded to the vessel's bodies, the materials must be the same to prevent galvanic corrosion. On the other hand, when the vessel's body temperature goes down up to minus 62 degrees centigrade, or process minimum design temperature, all the connected components such as supports will face the same temperature. As a result, the supports and skirts MDMT, or minimum design material temperature, would be also minus 62 degrees centigrade. To tolerate this cold temperature and to prevent galvanic corrosion, the best candidate material would be ASTM A516 grade 16 normalized, with impact testing at minus 62 degrees centigrade. Finally, the gasket material needs to be specified. As the flange rating is below 600 pound, the gasket types is a spiral wounded, and as usual, its material on inner section would be 316, which can tolerate our process minimum design temperature. As you noticed, when we are looking for bolted internal materials, stainless steel 316 materials, almost all manufacturing types can withstand our low temperatures up to minus 200 degrees centigrade or colder temperatures. Accordingly, a stainless steel gasket would be a good choice here. Now this table is completed and almost all the required materials for a vessel working at low temperatures is specified. As you noticed, in some cases, we prefer to control the cost and time of the project in purchasing the raw materials, such as shell plates, which we selected a commonly used material, ASTM A516 grade 16 normalized, with impact testing at MDMT. In other cases, we prefer to select the materials with the MDMT in the range of the minimum temperature in Table A1 of ASME B31.3, like the flanges, pipes, and fittings. In some other cases, we prefer to use the exemption figures based on our interpretations of the process conditions. Material selection in an overall view has a thin border between the interpretations and engineering calculations. To be an expert material man, you need to understand the process conditions and review all the standards and codes for an optimum decision. And here is the end of this tutorial. I hope this video helps you in your projects. Please like the video, subscribe to the channel, and comment if you have any questions. Thanks everyone.